In this video, I'm going to go over some calculus AB problems involving position, velocity, and acceleration using derivatives and integrals and all that good stuff. So our first one, Steven swims back and forth along a straight line path in a 50-meter long pool for 90 seconds. Steven's velocity is modeled by this wonderful equation there. Where t is measured in seconds and v of t is measured in meters per second. So the very first thing I'm going to do is enter that equation into my calculator, into my y equals, so that I can do whatever I need to with that equation. So we entered into the calculator, and then anytime I need to do something with it, we can just refer to y1. So part A, find all times in the time interval 0 to 90 at which Steven changes direction. So what we're going to do is graph this equation. For my window, since we're going from 0 to 90, we want to see 0 to 90. And we're looking at the velocity. So if he's going to change direction, that means my velocity is going to change sign. So it's going to go from negative to positive or positive to negative. So I want to make sure I can see both positive and negative values. I don't really care about max and mins at this point, so just where it crosses the x-axis. I'll go ahead and graph. Okay, so here's our graph, and my velocity is positive to this point and then negative at this point. So what I'm going to do is I'm going to calculate the 0 there. Okay, so it wants a point on the left of it. Then I'm going to go until we see some negative values, and the guess doesn't really matter. Okay, so we get a value of 56. So what we did is we figured out where v of t equals 0, which occurs at t equals 56. So why do we know that he changed direction? Because v of t changes signs. Okay. Find Steven's acceleration at t equals 60 seconds. Show the setup for your calculations and indicate units of measure. Is Steven speeding up or slowing down at t equals 60? Give a reason for your answer. So starting with the first part, we want to find the acceleration at 60. Well, what we have is our equation for velocity. So what that's going to be is the derivative of velocity at 60. Okay, so we're going to let the calculator do this for us. We go to our F2 shortcut menu. We are doing the derivative of y1, which is in our F4 menu. Oh, not there. At x equals 60. Okay, we want to be accurate to at least 3 decimal places, so negative 0.0360. Units. So the units here are meters per second. So the derivative is going to be meters per second, because it's the rate of change of the velocity there. Then it says, is Steven speeding up or slowing down? So we know that the acceleration is negative. I'm going to take a look at what's the velocity at 60. So I'm just going to evaluate y1 at 60, which gets me a negative 1.1595. Okay, well, if both my velocity and my acceleration are the same sign, then our person here is speeding up. Okay, so in words, Steven is speeding up because v of 60 and a of 60 have the same sign. All right, next, find the distance between Steven's position at t equals 80 and his position at t equals 20 and t equals 80. Show the setup for your calculations. Well, what I'm going to use is our integral. Okay, because just using the fundamental theorem of calculus, this definite integral is going to be the antiderivative of velocity evaluated at 80. Well, the antiderivative of velocity is going to be position. So this is going to give me the position at 80 minus the position at 20, which is the distance between the positions. So I'm going to use this here. Okay, back to our calculator. We want to do the integral from 20 to 80 of y1. So our distance is 23.238399. Okay, as long as you have 3 decimal places, you're good, but more does not hurt. So, okay, finally, find the total distance Stephen swims over the time interval from 0 to 90. Show the setup for your calculations. So total distance, we know that he changes direction at some point here. So there's a difference between displacement and total distance. For total distance, we want to use the absolute value of velocity, because if we're going one direction and then the other direction, we're adding both positive area and negative area. So throwing that absolute value fixes that for us. If we didn't have the absolute value, you'd end up with displacement. Going from 0 to 90, we can get the absolute value in that F2 menu, or it's in the math menu. So our total distance traveled is, thinking, okay, 62.164. I didn't ask for it, but I'll go ahead and put our units as meters. All right, our next example, a particle P is moving along the x-axis. The velocity for particle P is given by this equation. For 0 to pi, at t equals 0, particle P is at position 5. A second particle Q also moves along the x-axis. The velocity of that one is this equation. From 0 to pi again, at t equals 0, Q is at position 10. So I'm going to take a minute here and enter both of those into my calculator, putting this in y1, and I'll put this in y2. Okay, so we've entered in our equations. Okay. First it says find the positions of particle P and Q at t equals 1. What we have is the velocity and a known position for each. So we're going to use the fundamental theorem again. So I'm going to integrate from 0 to 1. 0 because that's the one I know its position, 1 because that's what I'm trying to find. Okay, this is going to give me my x position of P at 1 minus my x position of P at 0. Okay. This piece I'm going to get from the calculator. Minus our x position at 0, which we know is 5. Okay, this I'm going to get from the calculator. So we do the integral from 0 to 1 of y1 is where that equation is stored. And we get a 0.3706. I want to solve for this, so I'm going to take this and add 5. So my x of p of 1 is going to be what I just found plus 5. Probably didn't need a calculator for that. Okay, and then we're going to repeat that same thing for q. So the integral from 0 to 1 of vq of t dt is going to be the x position of q at 1 minus the x position of q at 0. Again, this is what I'm solving for, and I know the x position of q is 10 at t equals 0, and we'll get our calculator to do the work for us. So integral from 0 to 1 of y2 this time gets me that value. And then again, I'm just going to add that over. So my xq1 is going to be this plus 10. Part B, are particles P and Q moving towards each other or away from each other at t equals 1? Okay, well, I have their positions at 1, so just kind of thinking number line-ish. P is going to be lower than Q, because call this 5 point whatever, and call this one 8 point whatever. So what we want to do is look at their velocities. Okay. So I'm going to find the velocity of P at 1, and I'm going to find the velocity of Q at 1. So in my calculator, we're just going to evaluate Y1 at 1. And I'm going to do my velocity at -1. All right. So this one's greater than 0. This one's less than 0. So my P is moving to the right. My Q is moving to the left. And since they're relative positions, that Q is to the right of P, they are moving towards each other. So for my explanation, I'm just putting that P and Q are moving towards each other because P is to the right of Q, is to the left of Q, moving to the right, and Q is to the right of P, moving left, which means they are moving towards each other. Okay. Find the acceleration of particle Q at time t equals 1. Is the speed of Q increasing or decreasing? So we did something similar in the last one. A of 1. A Q of 1, to be specific, is going to be VQ prime of 1. Q is stored in my Y2. So I'm going to do the derivative of Y2 at x equals 1, which is 1.0268. We already know the velocity from the previous problem is negative, which means the speed is slowing down. Okay. So in words, the speed of the particle Q is decreasing because VQ of 1 and AQ of 1 have different signs. And then we have another total distance traveled between 0 and P. So it's going to be the integral from 0 to pi of the absolute value of Vp of t. Okay, again, we're going to use the calculator. Make sure to use absolute values. When you do this, you're going to get 1.93148. So my last example, a particle moves along the x-axis with velocity given by that guy from 0 to 3.5. The particle is at position -5 at time t equals 0. So I have entered it into my y equals, so we can do all our good things. So find the acceleration of the particle at t equals 3. Acceleration at 3 is going to equal the derivative of velocity at 3. So do the derivative, y1 at x equals 3. Okay, and that's all we have for that one. Find the position of the particle at t equals 3. So we're going to again use that fundamental theorem because we know the integral from 0 to 3 of v of t is going to be the x position at 3 minus the x position at 0. We'll get this from the calculator. We are told our position here is -5. We'll get the integral from 0 to 3 of y1 gets me 3.2397, and then I'm going to add that -5. So my position at 3 is -1.7602. Okay, we're going to evaluate the integral from 0 to 3.5 of v of t and the integral from 0 to 3.5 of the absolute value. So first I'm going to talk about the context, because we've already talked about this. This is going to give me my total distance traveled. This is going to give me my displacement. So I'm going to go ahead and do the first one. So we'll do the integral from 0 to 3.5 of my function, which gets me 2.8439 is the displacement. Of the particle. From t equals 0 to t equals 3.5. Then we'll do the absolute value. And we expect a bigger number here because this is the total distance traveled. Okay, so again, it's the total distance traveled from t equals 0 to t equals 3.5. Okay, last part of this problem, a second particle moves along the x-axis and is given by position x2 of t is t squared minus t for 0 to 3.5. At what time are the two particles moving at the same velocity? Well, if my position here is this equation, my velocity is going to be 2t, minus 1. Okay, so what I want to know is where this equation equals my original given equation. So I'm going to go to my y equals. I'm going to have 2x minus 1 is my second equation. For my window, I only care about from 0 to 3.5. And I'll just go from like negative 10 to 10. Okay, so there's our first equation. And then we should see a line with a slope of 2 coming through. Okay, so the intersection is right here. So we're going to do second calc intersection, and I'm just going to enter, enter, enter. So my intersection, so my v2 of t equals v of t. This occurs when t is 1.5705. So these are some problems that involve position, velocity, and acceleration from the Calc AB course.